In this lesson, we will learn an important technique to improve the performance of a recursive program, and this technique is called recursion with memoization. Now, in a previous lesson, we had shown to you using the example of Fibonacci sequence that why recursion is not always good in terms of performance. Let's quickly have a recap of it. So Fibonacci sequence is defined by this particular recurrence relation. The first two elements in the sequence are 0 and 1, and all other elements are sum of previous two elements. And if we have to write a recursive implementation of this particular sequence, let's say we want to write a function fib of n that will give me fn from the above sequence. It goes something like this: if n is less than or equal to 1, we simply return n, else we return fib of n minus 1 plus fib of n minus 2. So we make two recursive calls, first to calculate fib of n minus 1 and then to calculate fib of n minus 2, and sum them up and return the value. Now if I make a call to calculate fib 5, and let's say I'll write f5 here for shortcut to fib of 5, then this makes a recursive call first to calculate f4. It also makes a call to calculate f3, but we will go in the order in which the actual program executes. So f4 makes a call to f3, f3 makes a call to f2, and we go on building this particular structure called recursion tree. So f1 and f0 do not make any further recursive call, and they simply return 1 and 0 respectively. This is a recursion tree. Now to calculate f of 5, we have calculated f of 2 thrice here, and similarly we have calculated f of 3 twice here. This is simply an overhead or redundancy, and for higher values of n, this increases the time and space taken by the program exponentially. So let's do something to avoid the recalculation of the same state or the same value again and again. So I will modify the function here in the left a little bit. So I will try to write this function fib of n again, and let's start with a base condition. If n is less than or equal to 1, we simply return n. What this basically means is that we already know f0 and f1. So anytime we are asked for f0 and f1, we simply return it and do not make a recursive call. So let's say once we find f2 or calculate f2 for the first time, we save it in the memory so that I do not recalculate it again. Similarly, any fn like f3, f4 and so on, once I calculate it for the first time, let's say I will save it in the memory. So in the program I will say something like, if fn is in memory, do not try to calculate it, simply return it. So we simply return fn, else we will first try to calculate fn by making recursive calls to calculate fib of n minus 1 and fib of n minus 2. And now I will first save this fn in memory so that I do not have to recalculate this again. And finally I will simply return this fn. We will show to you in an actual program how to store all this f2, f3 and fn in memory and return it as and when needed. Now let us see how this program now improves our previous recursion. Say we again want to calculate f5, and this makes a recursive call to f4. This makes a recursive call because we do not have f5 and f4 in memory yet. We have not finished calculating them even once. Now f4 again makes a call to calculate f3, f3 makes a call to calculate f2, and f2 makes a call to calculate f1, and f1 does not make a recursive call any further. So now at this stage, this f2 has finished calculating once. So now we save it in the memory. Now f3 also makes a recursive call to f1. Now after this returns, we also have finished calculating f3 once, so f3 is also in memory. Now f4 also makes a call to calculate f2 now, but f2 is already in memory now. So this particular recursion tree does not grow any further from here. We simply return from here because f2 returns the value from the memory. Again, F5 also makes a recursive call to F3. Now F3 has also been calculated once before and it is in memory. So F3 simply returns the value from the memory here, and the tree does not grow here as well. So what we are basically doing here is we are avoiding all the recalculation of the same state again and again. This particular implementation reduces the time complexity of this particular program significantly. So this is recursion with memoization. Let's now see in some real code how this works, and I will write some C++ for you. So here we have a simple recursive implementation of Fibonacci sequence in C++, and we have this method fib. This is the base condition, and this is the recurrence relation, and we ask the user for an n and print the result after calling fib of n. So let's see what happens if we run this program. Let's say we first give n is equal to 10. This gives me the result 55 immediately, and now let's give a slightly higher n, like n is equal to 40, and this time it's taking some time. It is still executing and I'm waiting for the result. Finally we get the result, but it took some time, a couple of seconds, to give me the result. Now let us try to write recursion with memoization and see what good it does to us. So what I'll do is I'll first declare an array f of size 51, and we will come back to why we have chosen the size 51 only. In the main method we go ahead and say that, hey, for all I from 0 to 50, set fi is equal to -1. So if fi is -1, we can say that fi is not calculated yet. In the method fib of n, we would say that if fn is not equal to -1, then definitely it is in the memory and it is already calculated. So we will simply return fn. Else we will calculate fn by this recurrence relation and then return fn. Now we have declared this particular array in global scope so that only one copy of it is created, and the same copy is accessible to all the calls of this method fib and method main as well. Now let us run this program and see what happens. Let's try this again for n is equal to 10, and we get an result as 55, which is correct. We also get the result in no time. For n is equal to 40, let's see what happens, and this gives me the result immediately. So recursion with memoization in this particular example is not as efficient as an iterative implementation in terms of memory, but it is as good as an iterative implementation in terms of time for larger values of n, and it is a lot better than simple recursion, which grows exponentially, the time taken by which grows exponentially with the input. So a couple of things in the program. We have declared the array of size 51 only. This limits us to calculating only the first 51 elements in the Fibonacci sequence if we are using recursion with memoization. You definitely need to make a call in recursion with memoization that what is the maximum value of input that you are giving, and accordingly you have to declare this array. We could also avoid writing this particular condition here. We could simply go ahead and in the main method we could initialize f0 as 0 and f1 as 1, and this particular condition, if fn not equal to -1, will take care of the previous condition that we have omitted or removed. So recursion with memoization is a very nice technique, algorithm design, and we will encounter more of it in coming lessons. So thanks for watching.